Hello, today we'll be talking about VAR Optimization implementing a smart inverter. So here we have a PV source, and the first step will be to implement the maximum power point tracking on it. So maximum power point tracking's goal is to extract the maximum available power from the PV model and making the voltage to its most efficient level to the PV to operate. So as we can see here, we have a simple circuit with a PV panel as a source. As we can see in this video, we're powering the system with a flashlight, and as we can see, the voltage level will change as close as we get from the flashlight to the PV panel. But for the purpose of our project, we decided to stick with a voltage of 150 millivolts. After that, we implemented the code that it was provided in Bitbucket. And then as we can see here for the output, each time the power is increasing until we get to the maximum level that we can get.
So next, we're going to be talking about the phase lock loop, and the phase lock loop is a control system that generates the output signal whose phase is related to the phase of the input signal. So the first part of the phase lock loop is the phase comparator, which basically compare the phase between the input signal and the signal that's already inside the system. And then it goes into the filter. Most likely it's a low pass filters. Low pass filters just make sure that every frequency is into the same frequency. And the voltage oscillator. And the voltage oscillator is an electronic oscillator whose oscillates frequency is controlled by the voltage input and applies to the voltage determined by the instantaneous oscillation frequency. So basically increase or the frequency in the phase, so to match up with the system phase. So for the next part, it's the result. I basically use analog discovery to measure the frequency measurements, phase measurements, and the phase lock measurements. I was able to measure the frequency, the phase, and put two signals together and lock their phases and frequency at the same time.
So for the next part, we are implementing the VVC algorithm. So based on the equations on the top left corner, this is how we defined our reactive power in a DQ0 reference frame. And then we're defining our Q star as being the targeted Qs that we need to generate to absorb or generate VARs. And then we derive the delta Q in between, and this is what we're going to be feeding in our PI controller to determine our signals to be sent for the PWM. The code on the right describes that procedures. So we're first calculating the Qs, and then we are taking a V reference to be 1 PU. That means that is at 120 volts. And then we'll be calculating the delta Q and then our Q reference. The KP and KI are gains for our PI controllers. And we are generating the IQ ref that will be sent through UART to the PWM control.
The last part of the smart inverter is the implementation of the pulse width modulation, and due to this being an alternating current signal, it's going to be done with sinusoidal pulse width modulation. I implemented this on the STM32 processor board. As you can see here, there was a sine wave that was generated using the DMA, which is direct memory access. So the values, 360 values of the sine wave were calculated and stored in the block RAM on the board, which is the DMA, and then it was converted into an analog signal through the DAC, which is the digital to analog converter on the board. The sine wave from the DAC was then brought back into another pin and captured in a pin that was converting from analog to digital, which is the ADC converter in the STM32. That signal, the digital values of that signal, were then used to kind of as a reference for the pulse width modulation to determine the duty cycle lengths. So as you can see in the picture here, there are pulse width modulated signals that last approximately the the entire duration of the magnitude of the sine wave signal.